So, we are discussing the design of single tune filter. So, let me go to the diagram that we considered in the last class. So, it is the graph of the semicircle where it is shown as a plot in the plane where I have one axis as the real part of the admittance of the filter GF BF. So, we derived some conditions so far. So, we saw that one has to draw a tangent to the semicircle which makes an angle phi m. So, let me draw that tangent. So, this dotted line makes an angle with respect to the boundary uh, which is equal to phi m. So, this is y of h. And to get YNH, what I should do is first take YFH plus YNH, which is obtained by dropping a perpendicular from the origin to the boundary. Okay. So, this is YFH plus YNH. This is 90 degrees. So, from this I get YNH. This is YNH. Now, if I take this angle, what is this angle? It is phi m. Okay, so that should be clear. Okay. Now, if I take okay, I need to use different colors, otherwise it will cause confusion. Suppose I take this angle. What is this? 90 minus phi. So, 90 degrees minus phi. So, from that I get other, suppose I take this angle phi m. It is visible. If not, I will use a different color. Now I will take yes, the center of this semicircle. Okay. So the center of the semicircle is on the BF axis. Of course, I already said what is the diameter of this circle. The diameter of this circle is 1 by 2 delta max into square root of c by L. So that is the diameter. So if I take the distance from this point to this point, so this diameter is 1 by 2 delta max square root of c by L. Now, if I take a straight line segment from the center of this semicircle to this point at which I have taken the tangent. Okay. So, please note I have taken the tangent here. So, what is this angle? This is a right angle. Okay, that's a right angle. Okay. Now, what is this angle? See, I have dropped two perpendiculars to this boundary, one from the origin, one from the center. So, both are parallel. See, there is one perpendicular dropped from the origin to the boundary, one perpendicular dropped from the center to the boundary. So, these two are parallel. So, if the other line is making an angle phi m with respect to this BF axis, this is also phi m. See, this is phi m, means this is also phi m. Then if I take this angle, what is this? What is this angle? Phi m by 2. Recall what you would have studied in say 8th standard or whatever, school geometry, nothing more than that. Phi m by 2. Okay. So, if that is phi m by 2, then if I take this angle, the green one, this is phi m by 2. The green, this one, phi m by 2. Okay. So, this is same as the diagram that we considered in the last class. I have made some additions. I have shown a few angles additionally. That's all. Okay, and there is one more line segment from the center of the semicircle to the point of tangent. That's all. Nothing more than that. Okay. Now let us continue our discussion of design of single tune filter. So we said that we have to minimize the cost of the filter, minimum cost filter. So we got the expression for the reactive power rating of inductor. So we got QL, the reactive power rating, as, so what was the expression? Can did I get this expression IF1 squared by H under root L by C plus IFH squared into, I mean towards the end of the last class I got this, okay. So that is the reactive power rating of the inductor. Similarly, if I take the reactive power rating of the capacitor, so if I just ignore all the harmonic components other than the harmonic component for which the filter is designed, then the only fundamental component of the current and the relevant harmonic component is to be considered. So, there is a reactive power rating due to fundamental, that is IF1 squared into reactance. What is the reactance of the capacitor at the fundamental frequency? Yeah, 1 by, now we do not have a notation for the fundamental angular frequency. So, we have a notation for the harmonic omega h star. So, omega h star by h is fundamental into C in the denominator. So, this is due to fundamental. Similarly, due to harmonic component, it is IFH square into 1 by omega h star C. So, this can be written as, so if I use the equation omega h star is equal to 1 by root LC, I get IF1 square into H into L by C plus IFH square into root L by C. See, what I have done here is I use this C expression for omega h star 1 by square root of LC. That's it. Okay. Now, if I ignore the cost of resistor, so far I have not said why the resistor is required, but we will see that the cost, I mean resistor is in fact required, and but the thing is the resistance is very small, otherwise there will be loss. See, any resistive component should serve some purpose, but at the same time, I mean, it should not be unnecessarily added. So, if at all it is added, I mean, it is a very small value for serving something, but not contributing to loss. So, if cost of resistor is neglected, then cost of filter. So, filter has three parts: resistance, inductance, capacitance. So, if resistor cost is neglected, then the cost of filter is due to cost of inductor and cost of capacitor. So, I will use a notation for this cost of filter as K. I can't use C because C is already used for capacitance, K for cost of filter. So, cost of filter is cost of inductor plus cost of capacitor. So, the cost of inductor is proportional to the rating of the inductor. So, I write this as QL into UL plus the cost of capacitor is QC into UC, where UL and UC are unit costs, that means cost per unit rating. Okay. So, UL and UC are unit costs of inductor and capacitor respectively. So, if I want to look at the expression for cost, it is in terms of QL and QC. UL and UC are constants. So, QL and QC are dependent on IF1 and IFH. See, essentially we want L and C. Suppose V1 is the RMS value of fundamental component of the voltage, is RMS value of fundamental component of voltage across filter. Okay. Then can I get an expression for IF1? Did I define IF1 in the last class? IF1 is the RMS value of fundamental component of the current through the filter. So, can I get an expression for IF1 in terms of V1? It is the fundamental voltage divided by the impedance, magnitude of the impedance. What is the magnitude of the impedance? 1 by? Okay. Can I write it in terms of, say, Y of H is something which I do not know. See, when I am designing a filter, I want to find the value of L and C. So, as I said, we will do a minimum cost filter. We will try to minimize k. So I will write k in terms of L and C. So k is dependent on QL, QL is dependent on IF1. So IF1 should be written in terms of L and C. So what should be the expression in terms of L and C? Root of? Okay. Okay, let me make one assumption. Let R be neglected so that it's simplified. So it's the impedance is only due to L and C. I also already neglected the cost of resistor. I am also neglecting the value of resistor in computing the current. Okay. So what is the expression for the impedance? Magnitude of the impedance, not the complex one. L omega h by h. Okay, let me. Okay. So you are saying omega h star by h into L minus h by c omega h star. That's what you are saying. Mod. Now that you are saying mod because you don't know which one is larger than the other. But don't we know which one is larger among the two? First one means omega, the reactance of the inductor is larger or reactance of capacitor is larger? See, there should be the reactances of the inductor and capacitor should be same at what frequency? Resonant frequency, that is harmonic frequency for which it is designed. Now I am computing the fundamental frequency, impedance or admittance, whatever. So at fundamental frequency, which one will have a higher reactance? Capacitor or inductor? I will repeat. Now the capacitor and inductor will have the same reactance at resonant frequency. Fundamental frequency is lower than resonant frequency. So capacitive reactance will be larger. So I don't need this modulus. I know which one is larger. So I want IF1 to be positive because IF1 is an RMS value. Please note IF1 is an RMS value. That's why I want it to be positive. So I can use the knowledge of which among the two reactances is larger and straight away write the expression. So I will write this as, okay. So okay, I need not actually erase this. I mean, I could have taken that also. Omega h star L by h minus 1 by h by omega h star into c modulus. So since we know which one is larger, we could have just written this as Vh by h by omega h star c minus omega h star L by h. So if I use the expression for omega h star, which is 1 by root LC, I get IF1 as V1 divided by h into 1 by omega h star c is nothing but root L by c. Minus 1 by omega h, again omega h star is 1 by root LC, so it is minus 1 by h root L by c. So my intention is to write it in terms of L and C. These are the two quantities that have to be determined. So this can be written as 1 by root LC is a common factor in the denominator. Root L by C is a common factor in the denominator. Okay. So this can be written as 1 by square root of LC into V1 h divided by h square minus 1. Okay. Now if you look at either QL or QC, there is not only IF1, IFH is also there. So there is an IFH, which is the RMS value of the current of harmonic order H. Now how to get IFH? Can I write IFH in terms of IH? say if we considered one particular circuit, if you just recall, there was a representation of the converter in the form of a current source. I mean, we started with this only. Then the filter is represented by an admittance, the network is represented by another admittance. So, the magnitude of the current from the converter is IH, then the filter has an admittance Y of H at the harmonic frequency. Now, we are considering only harmonic frequency. The network has an admittance Y and H. So, can I write I of H in terms of IH and of course, and Y of H and Y and H. So, what is I of H in terms of IH? It is equal to IH into what? Y and H by? That is, there is something wrong there. Say, you have to just take all the voltages across the current source or voltage across the any of the admittances, they should be same. Okay. So, that will be the voltage magnitudes will be same if I write this as I of H equal to IH into Y of H magnitude divided by Y of H plus Y N H absolute value. Just divide this equation by Y of H. On both sides, what do you get if you divide by Y of H magnitude? You get the magnitude of the voltage at the harmonic frequency, that is VH we get. VH was the notation that we used in the last class. Okay. So, this can be written as IH. Now, come to this figure that we have just considered. Okay. So, this figure. Now, look at this ratio. Y of H by Y of H is one quantity and the ratio has one more quantity, magnitude of Y of H plus Y N H. So, these two quantities are actually the sides of a right angle triangle. Y of H magnitude and magnitude of Y of H and Y N H, Y of H plus Y N H. So, I can write that ratio as what? In terms of phi m, can I write? Cos phi m by 2. So, this is IH by cos phi m by 2. So, IH is a constant which is known, phi m is a constant which is given. So, I of H is a constant. Please note, when you look at the expression for I of 1, V1 is a constant, H is a constant, because V1 is the value of the RMS value of the fundamental component of the voltage, and H is also a constant. Similarly, in the expression for I of H, IH is a constant, phi m is a constant, but I of 1 is not a constant because I of 1 is dependent on the unknown quantities L and C, whereas I of H is independent of the unknown quantity L and C. Is that clear? So, I of H is not dependent on the unknown quantities L and C, only I of 1 is dependent. Okay. So, what I will do is, wherever there is I of H, I will retain as it is. Just now we showed that it is a constant, whereas it is independent of L and C. So, this is independent of L and C. Whereas I of 1 is dependent on L and C. Okay. So, let me get back to the expression for cost. So, the cost K is the inductor rating into unit cost. So, if I take the inductor rating QL, so QL has two terms, I of 1 square. So, I substitute the expression for I of 1. So, just now I derived the expression for I of 1. Okay. So, yeah, let me just give a few more steps. So, it is I of 1 squared by H into root L by C plus I of H squared root L by C. This is QL, this should be multiplied by UL plus the reactive power rating of the capacitor is I of 1 squared H into root L by C plus IFH squared into root L by C into UC. So, this is the cost of the capacitor. Now, what I will do is I will just substitute the expression for IF1 that we just derived in this expression for cost. So, I can write K as, so substitute for IF1. IF1 is 1 by root L by C into V1 H by H square minus 1. So, what I get is V1 squared. So, there is an H, but H gets multiplied. Sorry, H, I mean there is a H in the denominator also. So, that results in V1 squared H divided by H square minus 1 whole square, and there is a 1 by root L by C in the expression for IF1. So, and of course, in the cost expression also I have a root L by C. So, effectively it results in 1 by root L by C into UL. So, that is the first term. Say the cost has 4 terms, 2 due to inductor, 2 due to capacitor. This is the first term. The second term I write that as it is, because IFH is independent of L and C. Okay. So, I am just substituting the expression for IF1. Similarly, if I take the first term in the cost function of the capacitor, again substitute for IF1. So, I get V1 square, now there is H cube now divided by H square minus 1 whole square into 1 by root LC, 1 by root L by C into UC plus IFH square root of L by C UC. Okay. So, is this okay? Just substituting the expression for IF. Okay. So, that gives an, I mean I will try to simplify this. So, I will write this as, I will try to take the terms from coming from the fundamental and together. So, they have a common factor, V1 squared H divided by H square minus 1 whole squared into 1 by square root of L by C into UL plus H squared UC. I am taking the first term and the third term in the previous expression, plus the second term and the fourth term has a common factor, IFH squared root L by C into UL plus UC. So, essentially there are 2 terms. So, if you look at this expression for cost, look at all the quantities. V1 is constant, H is a constant, UL is a constant, UC is a constant, IFH is a constant. So, the only unknown quantities are L and C. Okay. Now, I can say that the only unknown quantity right now is not just 2, but only one, which is L by C or square root of L by C. I can say square root of L by C is an unknown quantity. So, if I want to minimize cost, the necessary condition is the first derivative of cost with respect to this unknown quantity square root of L by C should be 0. Huh? Both of them should be equal. Yeah. Let us see. Suppose I take the first order derivative. So, what do I get? So, from this I get an expression for L by C or root L by C. That is all I can get that. So, if I take the derivative, what do I get? Please note we are taking the derivative with respect to square root of L by C. Square root of L by C. So, can I say that the derivative of the first term in the expression for K is minus V1 squared H divided by H square minus 1 whole squared into UL plus H squared UC into what? into what? The derivative of the first term, C by L, okay, into C by L. So, or 1 by L by C. Then the derivative of the second term is easy. It is just I of h square into UL plus UC. We are differentiating with respect to square root of L by C, that's all. Okay. Now, what does this give? This gives the value of L by C. This is actually giving the value of L by C from the necessary condition. So, from this I can say, from the necessary condition for minimum cost, L by C should be equal to V1 squared H into UL plus H squared UC divided by I of H squared into H square minus 1 whole squared into UL plus UC. Is this okay? Now, this is a necessary condition, but whether it gives minimum or not is yet to be determined. So, how do I find that? I have to take the second derivative and see whether it should be what? Second derivative evaluated at this value of L by C should be positive. It should be positive. We are minimizing. So, if I take the second derivative of K with respect to root L by C. So, and this should be evaluated at the value which is just now obtained. So, what is the expression for the second derivative of K? We have the first derivative of K. So, differentiate it again with respect to L by C. So, if you look at the first derivative expression, the second term in the first derivative is independent of L by C. So, what I get is 2 times V1 squared H divided by H square minus 1 whole squared UL plus H squared UC into 1 by square root of L by C to the power of 3. Now, you put any non-zero value, I mean any not any non-zero value, any positive value for root L by C, you will see that this second derivative is positive. Now, please note, you look at the expression for L by C, this L by C is positive. I mean, otherwise it does not make sense. L is positive, C is positive, both should be positive. So, okay, so this is greater than 0. So, it satisfies the sufficient condition. Okay, but it still does not give value of L and C. It gives the ratio. It just gives the ratio. So, how to find L and C? For Y of H is even more complicated. Y of H means you should know R also. So, omega H star is 1 by root LC. So, I use these two equations. So, I have the expression for L by C. I also have the expression for omega H star. Omega H star is known. Please note, omega H star is known. So, from this I can say that, so what I do is I write this as the previous equation as L equal to C into V1 square H into UL plus H squared UC divided by I of H squared into H square minus 1 whole square UL plus UC. Okay. So, I use this expression for H and substitute it in the expression for omega H star. So, what do I get? 1 by C into square root of I of H square into H square minus 1 whole square into UL plus UC divided by V1 square H into UL plus H square UC. So, this equation will give me what? Value of C. I know the left hand side omega H star and I know the coefficient of 1 by C. All quantities are known. So, I get C. Once I get C, I can find L. Once I can find L and C, can I find R? Yeah, how? So can I relate R, GF and BF? What is R in terms of GF and BF? See, it is the real part of the reciprocal of y of h. Real part of the reciprocal of complex y of h. So can I write this as GF divided by what? GF divided by GF square plus BF square. Now again come to this figure. Please not yes. How y of h is known? Come back to this. Now, how to determine y of h we discussed in the last class. If you recall, we take delta max, the worst value of delta max, get this semicircle. So, from this semicircle, can I get the value of okay. How did we determine y and h? We know how to determine y and h. We determined the value of y and h from the boundary, and we got y of h from the tangent. Yeah, I didn't get what exactly you are asking. How to get y of h? How we get? Yeah, how we get y of h? How we get y of h? Can we get this semicircle? See, just now I said how to find. See, delta max, we take the worst value. So, how do we get the semicircle? See, for drawing the semicircle, I need this diameter, no? So, do I know the diameter? How? Just now we determined. Root c by L we just now determined. So, I know how to find the diameter. So, I know how to find the semicircle. So, if I know how to find this semicircle, then what should I do? How to get, yeah, the question is still valid. See, till now I have not said how to get the diameter. We just know is how to get the diameter. So, once I know how to get the value of the diameter, I know how to draw the semicircle. So, how to get y of h? I mean, it's a question still, I mean, it's not completely answered. Yeah, how to get y of h? Radius of the? Yes. So, from that you get, okay. So this figure will help in, I mean, getting all the quantities. Now, if I take GF, see, please note GF is the real part of y of h. So, can I say GF is y of h into cosine of some angle? What is that angle? See, if I just project y of h onto the GF axis, I get the value of real part GF. 90 minus phi m by 2. So, okay, let us write that. So, GF is the magnitude of y of h into cosine of 90 degrees minus phi m by 2. Okay. So, that is GF. Now, what is GF square plus BF square? It is nothing but the magnitude of y of h square. Okay. So, cos 90 minus phi m by 2 is sin phi m by 2, and this y of h in the numerator, the magnitude of y of h in the numerator gets cancelled. So, we are left with y of h magnitude in the denominator. Okay. So, this is sin phi m by 2 divided by, what is y of h? Yeah, again use the figure. So, if you look at this figure, okay. So, okay, let me draw one more line segment which will be easy to answer this question. I will take this line segment. Okay. What is the angle between this red line and this? 90 degrees. So, this is 90 degrees. So, from this diagram, I know two, I mean, I know that the hypotenuse is 1 by the diameter, 1 for this triangle, right angle triangle. See, I take this red line and the just newly drawn straight line segment and another one line segment as the diameter. These three form a triangle. So one side is 1 by 2 delta max root c by L, another one has a magnitude y of h. So from that, can I say that y of h is the diameter into cosine of some angle? That angle is phi m by 2. So y of h is 1 by 2 delta max root c by L into cosine of phi m by 2. So finally, I get the expression for R as 2 delta max, if I do simplification, into root L by C into what? Tan phi m by 2. So I know all these quantities. Delta max is known, it is the worst value of delta. L and I know, just now I found L and C. So we know how to find L and C, and phi m is given. So from that I get R. So this is a single tune filter. It's a simplest possible design by making some assumptions. Okay. So first of all, we made the assumption of ignoring the variation of the values of inductance L and C itself. So we designed this filter by just considering the variation of the system frequency, that's all. So if we consider even the variation of L and C, it becomes even more complicated. Okay. So this is the simplest possible design, but we will not go to anything beyond this. So this is what is known as single tuned filter.